Hello everybody. Today we will be taking a look at how to solve LeetCode problem 124, binary tree maximum sum path in Java as well as in Python. You can find the link to the problem description below if you don't have it. This is classified as a hard problem. However, what makes this problem hard is the concept and the visualization, and not so much the implementation of the solution. So let's get right to it and take a look at what the problem is asking from us. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting to them. A node can only appear in the sequence at most once. So this is bolded, and I assume it's important, and looking at it, we can see why it will be important. So taking a look at this, we can kind of see that a path is just going from one node in the tree to another using the edges in the binary tree. So if we're starting in node 2, to get to 3, we would have to go to 1, and then we can get to 3. So this means a path can't jump from one child node to another without going through that subtree route. So what does that mean? That basically means we can't go from 2 to 3. To go from 2 to 3, we have to go through 1. And also what's interesting here is because it's the part it says that each node can be used only at most once, looking at the second example here, we can't take the sum of this whole tree. Because if we took the sum of this whole tree, let's imagine we're taking a path starting at 9, -10, 20, and then once we get to 20, if we take 15, we can no longer take 7, because to get to 7, we'd have to go back to 20. And vice versa for 7. Okay, so in that case, we can kind of see that a path is just going down one side of the tree from a root to the other. All right, let's continue looking at what the problem is asking. The path sum of a path is the sum of the node's values in the path. Given the root of a binary tree, return the maximum path sum of any path. So looking at example 1, we can imagine if we had all the paths of the tree available to us, it wants us to return the path with the maximum sum. So looking here, we can see that the maximum sum path would have to be 2, 1, 3. This sequence here would give us a sum of 6, which is the maximum path in here. Now let's look at example 2, which is a little more interesting. Over here, we can see that we shouldn't take -10. Because if we take a path from -10, let's just say we take 9 and -10, so far we have -1, and then we take 20, then we're going to have 19, and then whatever else we take, 15 or 7, the total sum is going to be less than if we just simply took the path 15, 20, and 7, which adds up to 42. Okay, so now that we can see what the problem is asking from us, how do we begin to approach this? I think a good start for this might be to start visualizing what this looks like and how we can solve this problem for a leaf node, a subtree root, and then how we can use those cases to solve it for the whole tree. So I've drawn an example 2 over here, and let's go through the tree here to break down the problem into smaller, more manageable chunks. So we know just by looking at the maximum path sum for this example here from earlier that the answer would be going through this path here, 15, 20, 7 for 42, or 7, 20, 15, either way, it still ends up being 42. But how do we go about computing this efficiently in the tree, right? Well, before we start computing this efficiently, let's just imagine what a brute force solution would look like. So in a brute force solution, we would have to go through all the possible paths in this tree. So every single node by itself is a path. And then we would calculate all the other paths we can make. So for example, 9 to 10 would be one path, 9, 10, 20, and so on, and so on. Once we have a list of all these paths, we would then simply go through each and every single one of them, find the sum, and return the maximum sum of the paths. So from this, we can observe that given any path, there is going to be one node that can be considered the parent or the grandparent, of all the nodes in the path. So for example, in 9, -10, it's going to be -10 is considered the parent or the grandparent of all the nodes in the path. If we consider 15 and 20, 20 will be the parent or grandparent of all the nodes in this path. 20 will again be the grandparent or the parent of all the nodes in the path if we consider 15, 20, and 7. So this observation here kind of alludes that maybe to get the maximum path sum, we need to consider every single node to be the starting point of our maximum path sum. So let's now run through this example and do this. If we consider 15 to be the starting point, then, well, there's nothing on the left of 15. There's no nodes on the right. So the maximum path sum for just 15 is 15. And this is going to be true for all leaf nodes. Now for 20, it's going to be itself, right, plus whatever's on the left, 15, and whatever's on the right, which is 7. Which is 42. So far so good, right? Now if we imagine -10, well, this is going to be -10 plus what's on the left, which is 9, plus what's on the right, which is 42. And what do we get? We get 41. Okay, so it seems like we have a working solution here, where our maximum path sum here is 42, and everywhere else we calculated it is less than 42, so great. But there is a bit of error in the way we're doing this right now. And we can kind of see this error better if we imagine that instead of -10, we had here -8. Right? So now if this was -8, then our final maximum path sum, given our starting node of -8, would actually be 43. But does that actually make sense? Would that actually be true? Well, for this to be true, this would mean that our maximum path sum would be this. It would be the whole tree. And right away we can see the problem, because we saw this in the beginning, that we can't include any node twice in our path sum. And to have this whole tree as a path sum, some node will always be included twice. So for example, if you started from 9, -8, 20, and then went to 15, to get to 7, we would have to go back to 20 and then get to 7. So this kind of throws off our calculation slightly. So to fix this, what we want to do is, given any node as the anchor node, or the grandparent or parent of all the paths, we only want to find, we want to find the maximum path sum on the left and the right nodes, and then we want to return one side of the maximum path sum. So to give a more concrete example, what would this look like here? For -8, right? We want to return only one side of the path for both 9 and 20. So in 9, it's just a single node, so nothing really changes there. But for 20, instead of us passing the maximum path sum, which is 27 and 15, we only want to pass one side of it. So 20 and 15, or 20 and 7. So what does this look like? Well, this looks like we want to only pass in, so to pass this value upwards, if we're imagining, we only want to pass here root plus left, or root plus right, whichever value is greater. However, at the node itself, so at 20, to calculate the max path sum for 20, we want to use root plus left plus right to calculate the maximum path sum of this path. Okay, so far we seem like we're getting towards a working solution, which is when we're at that node, we're going to consider the left, the right, and the root to get the maximum path sum. But when we're passing a value back up to the node before it, we're only going to pass in one side, so root plus left or root plus right. Now there are some additional things we got to consider here. And one of them is that we don't necessarily have to take the left and right nodes. We should only take the left and right nodes if they increase our maximum path sum. So if we imagine for 15 here that we had two other nodes, right? They're wobbled, but you get the gist of it. But let's imagine they were -2 and -1. In this case here, for the maximum path sum at 15, it's best to not take the left or the right, because 15 by itself is greater than 15 plus -2 plus -1. So we need to actually have an additional check here when we're calculating our maximum path at the node. It's going to be root plus max, right, of 0. In this case, 0 implies we don't take the node, or we don't take the left or right node, of left, right, if I can spell left, plus max of 0 and right. Squeeze that in there. Great. So now this gives us the option of not taking the left if it's going to decrease our path sum, and not taking the right if it's going to decrease our path sum. And then finally, what we want to pass back upwards to 20 so it can calculate its maximum path sum is then only either root plus, double plus, max of 0 and left, or actually, never mind, that wasn't a double plus. My T's are just terrible. Max of 0 and right. Okay, so now we actually have a working idea of how to kind of look at this problem, and we can see that we have built up these recursive cases because each single one of these problems is a subproblem for the node on top of it. So to calculate the max path sum for 20, we need to calculate the max path sum before for 15, right? And then we only pass back one side of that path sum. Same goes here for 7. And then finally, we are also going to, even though we know the maximum path sum in this case would still just be 20, 15, and 7, once we calculate this, we need to pass this back up to -8. And then this is going to be calculated, its maximum path sum, to be sure that the maximum path sum is only 42, and there isn't some other path sum available. So now let's look at what our cases would look like. So our base case, in this case here, would be, well, if we are at a null root, right? If the node if the root we're at does not exist, then the maximum path sum can be 0, right? Which is we just take nothing because nothing is available. So base case, root is null, return 0. Then we want to get recursively what the maximum path sum for the left and for the right was, right? So let's say we have left, and then we are going to call recurse, or whatever the name of our function is, for the left side. And then similarly for the right side. Okay, so now we have recursively gotten the left and right maximum path sum for just one side of it. So we can assume that right now. We haven't actually done the logic to pass only one side of it, but at this point we can assume that we are going to in the future. Then we're going to have some variable, some global variable, which is going to hold the maximum path sum, right? And so we're just going to say in that case, right, that max path sum, right, is going to be the max between whatever was already inside of there and this we just said earlier. But to make this a little more legible, what we should actually do is we should just calculate the max here in left and right. So we should actually have max, it's going to be whatever we can get from the left, or 0 if we choose not to take it. And this is effectively going to be doing what we said over here earlier, of us not taking it if it's going to make our path sum be less. So in this case now, all we have to do is here just take whatever was in the root on the left and on the right. Great. So now we have calculated the max path sum for the current node we are on. Now finally, to do this, so all the other nodes can do the same thing, we actually want to pass only one of the paths up. And which path do we want to pass up? Well, naturally, we only want to pass one of the paths up. And we want to pass the path that is the greater one, right? It wouldn't make sense to pass up 20 and 7 because there is a greater path here of 20 and 15. So finally, we're just going to have a return of whatever is inside of the root, because to choose this path here, we have to take the root node value plus the maximum of left and right. Now, if both left and right decrease our path sum, these are just going to be the maximum of 0 and 0, which ends up being just root. Otherwise, it's going to be whichever path of left or right increases it more. And this is what's going to allow us to later or earlier on recursively calculate left and right. Okay, so now that we've seen our base cases, we've seen the visualization, let's actually start coding this problem now. Okay, so let's get started by implementing this problem. First, we can see here they have all these comments basically explaining the tree node class. And to access the left and right values, we have to use root.left and root.right, or whatever we name our tree node. And to access the value, we got to do .val. So let's just get rid of this to get rid of some of the clutter. And let's actually have our helper function, the one we were talking about for the base cases. Let's call it recurse. And in here, we're just going to take our tree node root, like earlier. And then let's start implementing the cases we spoke about. So if the root is null, right, we want to return 0. And then we want to recursively calculate the left and right node. So in left, it's going to be recurse root.left. So we want to find the max path sum for the left side. And we also want to have the option here of not taking it. So we add a check for 0 in case this ends up being negative. So we're just not going to take the left. And then same idea for the right. And now at this point here, we have calculated the left and right paths. And to get the max path for the current node we are on, we're going to have some variable, right, that we should define above. So max path sum. And let's, int. And let's give this some sensible value as -infinity or minimum value for integers here. This way it will always choose some value. We shouldn't do max path sum equals 0 because there could be the case that we have a tree that's all negative. In that case, we want to take the maximum path sum. That is just the least negative path so far. Then we just want to do max path sum, and we want to do maximum O is already in there before, so we don't want to overwrite it. The value in there is already greater versus whatever the value we are on currently, plus left, plus right. And this line here will now give us the maximum path sum for the current node. Okay, great. Now the final step in our in the process is to only return one side of the path. So we do that by passing in the node value itself, because again, to reach either the left and the right, we have to take root.val. And then we do plus whichever of these are greater. If both of them are negative, it's just going to be a max of 0 and 0, so we're not taking either. Otherwise, we're taking whatever path is greater. Okay, so now we just need to call our function and pass in the original root. Now these are going to make all the recursive calls. At the end of it, we're going to have to return whatever the maximum path sum it found. So let's try running this, see if we have any errors. Okay, looks like no syntax errors, which is always a good sign. Let's submit this. Boom, there you go, perfect. And the problem is solved. Now, to solve this in Python, it's very similar. Only real difference is really the syntax. So we want to first have our max path sum value, right? Which we want to start off at -infinity. And then we're going to define our recursive helper function. So recurse, it's going to be root. In this case here, it's just one of those things where we have to tell our function that when we say max path sum, it is not a local variable. So look outside of the scope here. And then we get to our base case. If the root is none, right, we return 0. And then we want to calculate the max of the left side, right, which is root.left, or 0 if we don't want to take it, or right. And, sorry, it's not DFS, I'm just used to saying that. It's gonna be recurse. And root.right. So now this is gonna go recursively to the left and right and find the maximum path, or we're gonna take 0 if the maximum path on the left and right was 0, or sorry, was negative. Then here, when you calculate the maximum path as max path sum and root.val plus left plus right. And then finally, to ensure we're only passing back one side of our max path sum to any earlier nodes, we just do root.val plus max of left and right. And there you go, we have defined our recursive function. Now all we need to do here is now we have to call it, and this is now going to recursively calculate our max path sum, and then we just have to return that value we got so far. So let's now try running it, see if we get any errors. No, we do not, and let's submit it. And there you go, this is solved. So there you go, we have now calculated the maximum path sum in Java and Python, and using the same logic, we can do this in any other language as well too. So hopefully you guys found this informative, and if you have, please like and subscribe, and I will see you guys next time.